Is it 11? It is 11. It's the last day. Rap horn, in case you forgot. All right, so we're going to get to where we get, which I think I know from the early class. So we're going to start off on kind of finishing up the elimination substitution stuff with talking about the Williamson ether synthesis. And this is kind of our standard way, wow. To make an ether. This is kind of the stock way that we make ethers. It's like 100 years old, but it's still one of the best ways to do it. So you take an alcohol, you react it with a base, and then an alkyl halide, and you make an ether. So this carbon here is that carbon there. So our base, we have two options for this. We have sodium hydride, which is like a legit base. And then the other one is to just treat the alcohol with just sodium metal. And then for our alcohols can be primary or secondary. And then our halides, we are limited again to, they can be methyl, primary, or secondary. But I said secondary and I wrote tertiary. Professional, doctor. All right. So the way this works is, right, you have your alcohol. Step 1, you treat it with your base. Step 2, you add your halide. You're going to make your product. All right, step 1, your alcohol reacts with your base and makes, bless you, and alkoxide. Right, which could also just be written as O and A, right? O minus Na plus. Right. And then from there, the O minus is our nucleophile, right? And it's going to do an SN2 reaction, right? It's going to attack the carbon that has our halide and push that halide off to give us our product.
I was asked to explain what happens in step 1, how that deprotonation occurs.
From here to here, what happened? Right, so you have NaH is H minus Na plus. The H minus grabs the hydrogen and pushes electrons onto the oxygen. So the byproduct here is you make H2 gas. Now, if you have same thing or something similar, right? And you use just sodium metal. Right. What happens here is you end up with, again, a sodium alkoxide, which is your step 1. And then once you're at that point, it's the exact same thing, right? You just got to the same O minus 2 different ways. One with sodium hydride, one with sodium metal. And then you're going to displace and make your product. So we all have YouTube. So we've all seen what happens when you throw sodium in water, right? It fizzes around for a little bit. And if it goes long enough, or you have a big enough chunk of sodium, it'll catch fire. That's because sodium reacts with the OH of water, right, to make sodium hydroxide, and it generates hydrogen gas. And then the reaction is exothermic. It gets hot enough that it ignites the hydrogen gas that it generated in the reaction. We're doing the same thing here, but instead of having water, we have an alcohol. So the OH of the alcohol, the sodium reacts with it to turn it into H2 gas and to make our alkoxide, or O minus. Right? So we can't use a Williamson ether synthesis to make ethers with tertiary carbons bonded to the alcohol. Right, so we can't use a Williamson ether synthesis to make something like this. And the reason is if we think about the pieces that we would have to use to do a Williamson ether synthesis, they don't do SN2 reactions. So let's say we broke this bond, right? The right hand side of the green line would be the alcohol, right? So that would be this alcohol. And then the left hand side of that would be the halide, right? So we would have, right? Can tertiary halides do SN2 reactions? No. A Williamson ether synthesis is just doing an SN2 reaction. So I can't use a tertiary halide because they don't do SN2 reactions. Well, let's break the other bond. Let's break it over here, right? Now the left-hand side is going to be the alcohol. And then the right-hand side is going to be your halide, right? So let's think about what happens when we take our tert-butanol and we deprotonate it, right? It's going to look like that. This looks an awful lot like potassium tert-butoxide, right? And that was a big base, and those big bases can't do SN2 reactions, right? They're too big. They only do eliminations. So no matter how we break up this ether, we never end up with a piece or two pieces that can both do SN2 reactions, right? I can get a primary halide, does SN2 reactions. I can get a primary alcohol or primary nucleophile, will do an SN2, but the other piece just doesn't work, right? So we can't use Williamson ether synthesis to make this. Now, I asked this in the early class, and I thought it was a trick question, but I'll ask you guys. Since I can't make that ether with a Williamson ether synthesis, how could I make that ether, right? We could do a hydration of a double bond, right? So what if we had this double bond, and we treated it with ethanol and sulfuric acid, right? That puts the alcohol in the most substituted double bond, the most substituted carbon of the double bond. It would make the ether that we wanted. So we should be able to look at any ether that doesn't have a tertiary carbon on the oxygen and determine what combination of alcohol and halide would be best to use to make that ether, right? So let's say we had this ether, right? And we can break this bond, right? And that's going to give us a secondary halide and alcohol. Or we can break this bond, here. That'll give us a secondary alcohol and a primary halide. Okay. The kind of our guiding principle for which one of these is preferred is, when possible, use a primary halide, right? So you want to try to pick a primary halide whenever possible for a few reasons, right? So primary halides are the fastest for SN2 reactions, right? And slowest for E2 reactions. They normally only do SN2 reactions, which means you don't have to worry about competition, right? You don't have to be as careful with your conditions because you know your halide is predisposed to doing SN2 reactions. So you don't have to worry about the elimination competing with your ether synthesis because you've picked a halide that doesn't do eliminations, right? So this eliminates the possibility of eliminations. All right? So let's say I give you a problem like this. I'm like, hey, pick out the best combination, right? And then in the forward sense, you'd say, okay, I take my alcohol. I want to treat it with base. Then I want to treat it with my halide. Oops, actually make it a real halide. And that's going to be my product.
I was asked to explain kind of exactly what we were doing and why we were doing it for this part.
So, right. So if I asked you, hey, how would you make this ether, right? Or what's the best combination of alcohol and halide to make this ether? You could pick, hey, these are the pieces I want to use to make the ether, right? And then you could be like, all right, I know what pieces I want to use. Here's how I can make that ether. I guess this was a bromide before, whatever. But here's how I'm going to make this ether, right? So you look at the ether and you think, hey, how do I put this together? What's the best way to put this together? These two pieces. Then you can show here, this is how you put these two pieces together. So do I want to break the red bond? Or do I want to break the green bond if I'm going to make this ether? If I was going to make this. I want to break the green bond. So if I break the green bond, I get a secondary alcohol and a primary halide. If I break the red bond, I get a secondary halide and a primary alcohol. So this is the best combination of alcohol and halide to use. And then if I wanted to put them together, I'm going to show how they went together. I could say, hey, I take my alcohol, I treat it with a base, and then I add how many carbons were there? Sorry, 3. 1, 2, 3. Right. Then I add my halide, and I'll get my product. So for us, the sodium hydride and just using sodium metal are going to be pretty much interchangeable. They're going to get you to the exact same place, regardless of what you use. You're always going to get to that O and A structure, right? Where you're going to have O minus and Na plus. And then that you can add your halide to. Yes, sir.
I was asked if there's any limit to how long the carbon chain can be on the halide.
Nope, it can be as long as you want it to be. So there's no limit to how long that chain can be. I could put 100 carbons on there. It's fine. As long as I can dissolve it, I can do my reaction.
I was asked to clarify the halide rules that I had set out on the first slide.
Sorry, we're going way far back. So your halide can be a methyl halide, can be a primary halide, or can be a secondary halide. You would prefer to use methyl and primary because they can't do eliminations, right? But if you have to use a secondary, you can. Same with like the alcohols, primary and secondary, but you can't ever use tertiary. So they have to be one of those options. So like for like a methyl, you could have right? Remember ME is the abbreviation for methyl. So like your product or the option you have to pick for your product could just be the OME, right? Or it's the same thing as if it were just O and then just the one bond, right? So they're both communicating the same thing. The ME is saying there's a methyl here, and then I can just draw the methyl, right? Same thing. Right? Or, this could be just methyl iodide, a carbon bonded to an iodide. Same thing. So don't get like hung up on the abbreviations and whatnot. Okay. First thing we want to kind of do, right, is we want to identify which side of our ether came from our double bond, right? I think that makes it easier, right? So how many carbons do we have in the double bond? 4, right? 1, 2, 3, 4. So our alkene has 4 carbons. So it stands to reason the carbon chain on our ether that has 4 carbons more than likely came from the double bond, right? So 1, 2, 3, 4 verse 2, 3. Right. So pretty safe to say that our alkene became the left-hand side of our ether. Now, do you guys want to make this bond, or do you want to make this bond? We're going to make the red bond. Okay, so if we're going to make the red bond, that means that compound B needs to be an alcohol, right? Because the 4-carbon chain is, we'll be smart, making the red bond. So the 4-carbon chain, right? So we're going to break red bond, right? So the 4-carbon chain was an alcohol. Now, how do you turn an alkene into a primary alcohol?
I was asked why we picked the red bond to break as opposed to the blue bond since they both yield primary halides.
So in this case, it doesn't matter if you break the blue bond or the red bond because they're both primary. The first person to say red bond, and so that was one we picked. But we're going to do the blue bond here in a second. But if they're both going to be primary, there's no difference. So how do I turn an alkene into a primary alcohol? Hydroboration, right? So that's going to be BH3, H2O2, hydroxide, and water, right? So, right, that's how we make the least substituted, the anti-Markovnikov addition of our alcohol, right? Now that we've made our alcohol, now we just have to take 3 carbons, right, and have a halide. So have 1 bromopropane, right? So 2 steps, we're going to say, okay, 1 is pick a base, and then 2 is 1, 2, 3, bromine, 1 bromopropane. There we go. Now, there's two ways to do this, right? There's no difference if I break the red bond or the blue bond, and if I have a primary halide, right? I have a primary halide either way. So if I were to break the blue bond, you could do this a different way. So I'm going to redraw it. So let's come over here. Right, and this time we're going to break the blue bond. So if we break the blue bond, what does that mean that B has to be? It needs to be a primary halide. So in this case, it needs to be a bromine. Not just because I like bromine, because bromine is also the only halide you know how to put on the least substituted side of a double bond. It's got light with it. What else do I need other than light? Nope, not Br2. That's how you take an alkane and turn it into an alkyl halide. We need an alkene. Nope. Again, think about your double bond reactions. I'm preparing you for the final, both emotionally and educationally. What was BH3? No, now you're just like putting random stuff together. Some of the early classes like sulfuric acid. I'm like, no, stop. Right? Yes, HBr and H2O2. I'm gonna erase my dashes. HBr, H2O2. Right, so that's gonna make your least substituted bromine. And now I have to take my alcohol, right, and say, all right, I need to take my alcohol and I need to treat it with a base, and that will give me my alkoxide to react with that bromide. Now, if this was a normal, not dumpster fire semester, right? If I gave you something like this on the exam as like, a synthesis problem, both of these ways to do it would be right? Because either one gets you to the same thing. Now, because we're like matching fill in the blank stuff, I have to steer you a little bit more, right? So if you look at it, you're like, oh, there's two ways for me to do this. Cool, right? And you start down the path of, I'm going to make the primary bromide, right? If I don't give you that structure, right? If I instead give you the primary alcohol, I'm kind of forcing your hand. So I just have to make sure that I don't give you, of these ABC here versus red ABC, I just have to make sure I don't give you one of them, right? So if I don't give you hydroboration as an option, you can't make the alcohol, right? So you can't use that as your way to do the reaction, right? You have to do it the other way, right? You have to pick the path that had all of the reagents and all of the compounds, right? Even though there are two ways to do it, I would kind of like steer you towards one. But I would like not give you this. If that's not one of your options, you can't make B. So then you have to do it this way, which hopefully I've given you all the options for, right? If I don't give you all the options for both, then I suck. But hopefully I've given you all the options for them, right? My advanced organic test had some issues. So hopefully we'll do better. Right. So just be mindful of, like, if you kind of lock into one way to do it and then you don't see the pieces, it might not be that you're like 100% wrong. It might be there's another way for me to do this. I need to find the other way to do it with the parts that I have. Seem reasonable? Try and go back a slide. Boop. Sure. Yes. Exactly. So like when I'm making these, I'm being mindful of like I can't put that as a possible answer because that is another way that you could do this reaction. So like, let's say there were I'm trying to think here. Right, so for dihydroxylation, where you put two alcohols on where a double bond was, I can't give you both osmium tetroxide, hydrogen peroxide, and cold dilute KMNO4 as options because I can't tell the matching, or if I can, I don't know how, that, hey, either one of these is right, right? I have to make sure I only give one of them and like steer you in that direction as opposed to giving both, right? So if there were multiple correct answers, right, that you know from the semester, I have to make sure there's only one of them so that you're not like, well, this one's right and pick it, and it is right, but then I haven't set up the problem to like give you the points. So as of right now, 91 points on the exam is done. I've got 9 more to play with, and there are 2 synthesis problems of 7 blanks each. So 3 blanks, structure, 3 blanks, structure, blank, structure. So there are 2 of those. I told the earlier class, but wait till you get to organic too, and like your final synthesis goes to like double A. Yeah. You know so much more with organic too. It's great. All right. So we've got like 20 minutes left in the semester. And what I would like to do with that is give you just the most basic introduction to IR. What I have found is Zoom is a thief. I feel like I've apparently lost a minute or two every single lecture for the whole semester, and I didn't realize it. So I'm like a lecture or two behind where I should be. So I want to just give you an introduction to this next bit of stuff. Just so, as I told the early class, like you have a new pickup line. Hey, want to hear about IR? From what I've found, people of all genders love it. You're like, go on. So it's great. Really help your social life. Okay, so I want to talk about methods of structural determination. Right? In lecture, I get to just draw what the product of the reaction is supposed to be, right? I'm like, hey, you're making an ether. And I draw the ether. Cool. Right? In lab, though, basically, all things organic, you're either going to get an off-white solid to a white solid, or you're going to get a yellow oil to a clear oil. That's basically our range for organic compounds, right? Basically, you have like teeth that haven't been to the dentist and like Hollywood actress color teeth. Those are like the options you have. That's your color range. Like yellowy to white, right? How do you know that that white powder that you made is what it was supposed to be? You can't just snort all of it, right? So how do you know that what you made is what you wanted to make, right? And we use different ways to determine our structures. So there are 3 main ways that we use to determine if the colorless oil that we made is the thing we actually wanted to make and not something else, right? So the first way is to use IR. Spectroscopy. And what IR lets you figure out is it lets you figure out what functional groups are in your molecule. It's really good at telling you if you have a C double bond O. Do you have a ketone? Do you have an aldehyde? Do you have an ester? It's good to let you know if you have an alcohol in your molecule. So it's good at showing like kind of your basic functional groups. Right? Another way that we can help determine our structure is mass spectroscopy. Which is MS. Determines the mass. Yeah. It determines the mass of the compound. So it can either, depending on the technique that you use, it can just give you the mass of the entire molecule. So a lot of times for like biological molecules or like peptides or things like that, we use mass spec and it will tell us the mass of that peptide, the whole thing. There are other techniques that in addition to giving you the mass of the entire compound, it breaks your molecule into pieces. And so then you can find the mass of the whole molecule, and then you can look for specific fragments that you expect to be in your molecule to make sure that they show up. Like, oh, my molecule should weigh 200, but I should have a fragment that weighs 50. Do I see that fragment in my mass spec? So that can help to make sure you have the pieces that you want. Another thing that mass spec does is basically you can determine your chemical formula, right? If you get an accurate enough mass, you can figure out what combination of atoms can add up to be that mass. So it's the difference between your mass being 200 and your mass being 200.1234, right? There are way less atoms that add up to 200.1234 than there are that add up to 200. So you can be like, oh, there's only one set of atoms that can combine to make my mass to 4 decimal places. So I know that's my formula. So I know every atom that's in my molecule. Right, so the mass spec can tell you every atom in your molecule based on the mass. The IR can tell you what functional groups you have. And then the last piece is NMR. Right. It does. So the NMR will show you all the hydrogens in your molecule, right? All the different types of hydrogens. Right? It gives you functional group information by where they come along that scale from 0 to 10. So the thing you did in lab, right? You're like, oh, I have hydrogens at 4. Oh, that must mean they're beside the oxygen of an ester, more than likely. Oh, I have hydrogens at 7. They're probably on an aromatic ring. So you can get functional group information off of where they come on the NMR spectrum. You could also get structural information, right? And you get like molecular formula information, right? The integration is telling you how many hydrogens you have in your molecule, right? So you can figure out, well, how many hydrogens do I have? That gives you part of your formula. And then the peaks, the number of peaks, the singlet, doublet, triplet, that's telling you how many hydrogens are on neighboring carbons. So then you can start to piece together your molecule based on that. So you can start to build structures. You're like, oh, I have a CH2 that has 4 neighbors, and I have a CH3 that has 2 neighbors. Oh, that looks like an ethyl group, a CH2 beside a CH3. Right? And you can start to build structures and build pieces of your molecule. So all of this stuff together, the NMR, the IR, and the mass spec, allows us to determine if we've made the compound we want to make. Right? So kind of beyond just like, yeah, I made a yellow oil. That's cool. The procedure said make a yellow oil, and I did. But you don't know if it's the right yellow oil. So this is how we determine that. Okay. So I'm going to go over IR in the most like basic way possible. Right. So IR basics. The first thing that we need to think about or need to realize when we talk about IR is that bonds are not rigid. Right? So when we draw bonds, we just are like, oh yeah, there's a bond, right? But it's not like there's a steel bar between those two atoms and they never move. Bonds are kind of better modeled as if they were springs, right? So you can think that between your atoms, you've got this spring. And we can either compress that spring and push the molecules closer together, or push the atoms closer together, I mean, right? Or we can stretch that spring and we can stretch those atoms further apart. Right? So all the bonds are vibrating just a little bit. They're going in and out, in and out, in and out, or they're kind of moving in other ways. What IR does is IR just happens to be the right energy that can cause bonds to vibrate. So the light, the energy of light that is infrared, matches up with the energy needed to make bonds vibrate and go back and forth. All right. So what we're actually seeing when we take an IR is we shine light through the molecule, right, or through a sample of that molecule, and all the light that gets absorbed that doesn't come through that sample is being used to vibrate bonds, right? So these bonds are moving a little bit. You shine the IR light on them, and they really start going, right? Because they just put in more energy, right? So if we look at an IR spectra, right? IR spectra for organic, I'm going to draw it up first, right, are what are called, they're shown like this, they're percent transmittance. On the y-axis. So they're showing how much light gets through the sample. So you have 100% transmittance is at the top, and 0% transmittance is at the bottom. So what that's showing you is when you have 100% transmittance, there was no bond that absorbed light at that wavelength in the molecule, right? So when you have these peaks up at 100, no light absorbed, which means all the light was transmitted through the sample. right? You lost none of it. Right? When you have a peak, that means there was a bond that absorbed light at that wavelength to vibrate. The x-axis is wave number, which has units of centimeters to the -1. So whenever you have a peak, that corresponds to a bond or a group of bonds that were able to absorb light at that wave number, at that specific energy. And whenever you have the peaks that are up at the top of the spectrum, that means there were no, or the lines at the top, that means there's no bonds there that are absorbing that energy. And different functional groups have very specific ranges in which they absorb light, right? And that's how we're able to use the IR to determine what is what, right? So we divide, I should say wave numbers, the scale here goes from about 4,000 wave numbers to 500 on the far end. The IR spectra, we divide it into two broad pieces, kind of like right here, right? This is 1,000 wave numbers. From 1,000 to 4,000, so going this way, this is the functional group region. All right, this is where all of your functional groups are going to show up. This is where the peaks for, like I said, ketones, aldehydes, aromatic groups, alcohols, amines, they're all going to come from 1,000 up to 4,000. Then below 1,000, this is the fingerprint region. Now, because I'm not a million years old, I've not cared about the fingerprint region in my entire life. Basically, the fingerprint region, supposedly, every single molecule ever made has a unique IR spectra from 1,000 to 500, right? That chunk is supposed to be the fingerprint of every single molecule. I've not checked. Basically, I was born after 1960, so don't care, right? So basically, all you care about for the IR is the functional group region. Now, I could, in the last 3 minutes, desperately try to throw a bunch of numbers at you, but I'm not going to. What I will say is that slide 7 in the notes has a list of all the various functional group ranges where you would expect to see a C double bond O, where you'd expect to see an alcohol. So when you're doing your bonus IR homework, that might help you, right? So, but I'm not going to put any spectra on the exam because other than my bootleg, basically pencil in my mouth drawing of a spectra right here, you've not seen a spectra. And no Zoom. I did not put a pencil in my mouth. I did not take off my mask. All right. So with that, as of right now, like I said, the exam is 68 questions and growing. So I don't know, pack a lunch. I'm going to take it. I'm going to finish it up and take it later on today to give myself a sense of how long it is. But normally the final, people don't take the full 2 hours. So I'm anticipating it being about 2 hours. It's still going to open up tomorrow at 8 a.m. and you'll have till Saturday at 11:59 p.m. So you can find a time to take it while you're trying to travel and get back home and whatever. So with that, Thanks. We made it. So I'll have office hours later today. I'll be around via email if you need me. But yeah, good luck. Thanks for this semester. And I guess I will hopefully see all of you, black boxes or in person, in the spring.